Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, presents the conference. Estimation of Failure Parameters of Industrial Asset Maintenance. Markov Decision Process. Today, in artificial intelligence, it is the mathematical framework that underpins reinforcement learning, RL, that models an agent's sequential decision-making in a stochastic environment to maximize accrued rewards. According to Markov property, the future state depends only on the current state and action, not on the whole story. RL algorithms find an optimal policy, what to do in each state by learning from the states, actions, and rewards. The MDP is well understood when the state and the spaces for action are small. Bertsekas, 2007, and dynamic programming, PD, algorithms, such as value iteration, Bellman, 1957, and policy iteration, Howard, 1960, theat are standard techniques for calculating optimal policies. In large state space problems, exact DP is not feasible since computational complexity scales quadratically with the number of states. The text presents the summary of the life of the Russian scientist Andrei Andreevich Markov. His best-known contribution is theoretical work in the field of stochastic processes known as Markov chains, which today are considered an essential tool in disciplines such as economics, engineering, operations research, and many others. In probability theory and statistics, a Markov process is a time-dependent random phenomenon for which a specific property is fulfilled. The Markov property, or without memory, is one for which the conditional probability about the present, future, and past state of the system is independent. The most practical importance is the use of the assumption that the Markov property is valid to construct a stochastic model for this process. It is a simple way to introduce statistical dependence, in such a way that it allows the strength of the dependence of the different delays to decrease as the delay increases. The term Markov chain is often used to imply that a Markov process has a discrete state space, infinite or countable. Normally, a Markov string would be defined for a discrete set of periods, such as a discrete time Markov chain, although some authors use the same terminology where time can take continuous values. We can talk about different definitions about the first-order Markov processes. States, the conditions in which an entity or possible events are found. Trials, repeated occurrences of an event being studied. Transition probability, the probability of moving from state I to state J in a transition or period. Markov, first-order, processes, to be used as models of physical or economic processes, must have a series of characteristics. The probability complies with the Markov principle. Existence of a finite number of states. The probability must be constant with respect to time or period. The trials must be in equal periods. The diagram presents two cases of simple Markov chains, one describing customers in a market and one describing the evolution of the climate. Transitions indicate that the probability of migrating from one state to another is independent of states and transitions between states. The transition matrix must be estimated from the historical sample, which can be done with a mathematical programming model. The long-term study facilitates the understanding of the behavior of the system. In this case, the chain has two entrapment states, 7 and 8, which implies that in the end the system will end up in one of those two states. The key components of an MDP are states, the different situations the environment can be in, e.g., A robot's location, a game's board configuration. Actions, the choices the agent can make in each state, such as move north, east, south, west. Transition probabilities, the probability of moving from one state to another after taking a specific action, incorporating randomness. Rewards, the immediate feedback, positive or negative, received after an action, guiding the agent toward its goals. Policy, a strategy or rule that dictates which action to take in each state to achieve the objective. The diagram shows an example of a simple Markov chain decision process, MDP, with 3 states, green circles, and 2 actions, orange circles, with 2 rewards, orange arrows. Markov decision processes are controlled Markov chains along with an immediate cost function and optimization criterion. The document Linear Programming for Large-Scale Markov Decision Problems proposes to apply mathematical programming to solve the MDP. Markov decision process problem is well understood when the state and action spaces are small. Dynamic programming, DP, algorithms, such as value iteration, Bellman in 1957, and policy iteration, Howard in 1960, are standard techniques to compute the optimal policy. In large state space problems, exact DP is not feasible as the computational complexity scales quadratically with the number of states. A popular approach for large-scale problems is to restrict the search to linear space for a small number of features. The aim is to compete with the best solution within this comparative class. 2 popular methods are approximate dynamic programming, ADP, and approximate linear programming, ALP. This paper focuses on ALP. The image presents the summary formulation of linear programming to solve MDP. The machine life cycle, MLC, aims to establish the characteristics that define the productivity in multiple activities such as use, productivity and wear and tear of the asset because of its use. Recovery of productivity thanks to preventive and/or corrective maintenance activities. The questions to be solved. What are the main features to consider when investing in a machine? For example, do maintenance, turn the machine back on, replace it? How does the machine's behavior change throughout its useful life? The above serves as an input for determine optimal negotiation policies, buying, repowering, selling, and estimate the economic value of a machine's ratio. What are the main characteristics to consider when making decisions that affect the life cycle of machines? It is carried out using analytical methodologies to classify the different types of machine behavior patterns according to their technical characteristics and the working environment in which they operate. Objective, definition and recognition of patterns based on a historical sample of the experiences lived in the organization, or in other similar organizations. The main analytical methodologies are machine learning, Markovian processes, Markov chain decision process, artificial intelligence, neural networks and fuzzy logic statistical classification methods, clustering methods using mathematical programming, advanced probabilistic models using mathematical programming, data mining. The figures show the average loss with variance error bars of the constraint sampling algorithm run with a variety of sample sizes. The document Optimal Maintenance Policy with Markov Processes is a reference of the application. Markov Decision Processes, MDP, optimal maintenance policies are determined by modeling equipment deterioration and maintenance actions as a stochastic process that minimizes costs or maximizes system availability over time. The optimal policy is a set of decision rules dictating when and how maintenance should be performed based on the equipment's current state. In the model, both random failures and failures due to deterioration can occur. Equipment deterioration is modeled by occurring in k discrete steps. The time spent on each stage of deterioration is distributed exponentially with an identical mean of 1/k lambda 1. The time to failure due to deterioration is represented by an Erlangian distribution. For the application of the stage device, 2 types of configurations are described, and the parameters of the models are estimated. Maintenance is supposed to improve the condition of the component. Maintenance is modeled as a Poisson process with a parameter lambda, m. Maintenance times are distributed exponentially with an average of 1/mu, m. Repair is an activity that returns a failed component to its operational state. It is assumed that repairs after failure due to deterioration will always produce conditions as good as new ones with an average of 1/mu, 1, while repairs of random failures may or may not achieve this. This assumption could easily be relaxed. The F0 status represents random failures that can occur at any time, but not while maintenance is being performed. Repair after random failures is completed at a rate of μ0 and then returns to the D1 state. The state space diagram of the maintenance model is shown in the figure. In the transition matrix of states, where the sum of lambda I is the negative of the sum of all the remaining elements in row I, the set of steady-state equations can be solved as PAT is equal to 0 and the sum equals 1. Where P equals P1, P2, P3, P4, P5, P6, P7, P8 is the steady-state probability that the component is in state I and is not undergoing minimal maintenance. The solution to these equations is obtained by using a recursive approach. The probability a lambda m, availability that the component is in service is given by a lambda m is equal P1 plus P2 plus P3, where lambda I is equal to the negative of the sum of all the remaining elements in row I, where P1, P2, and P3 are the probabilities that the component is in service. Once the state probabilities of the model are calculated, the optimal value of the mean time to preventive maintenance lambda is calculated by taking the derivative of a lambda m with respect to lambda m and then equating it to 0. The solution to these equations is obtained by using a recursive approach. The following example illustrates the implementation of the model. Consider that the average random failure of a unit occurs once in 500 days and that the repair lasts 7 days. If the unit is not maintained, it would fail from deterioration every 1,000 days, on average. Also, the mean repair time is 14 days, and the minimal maintenance would take an average of half a day. Assume that all times are exponentially distributed and the number of stages of deterioration of the unit is 3. Maintenance is modeled as a Poisson process with a parameter lambda m. Maintenance times are distributed exponentially with an average of 1 per micrometer. Repair is an activity that returns a failed component to its operational state. It is assumed that repairs after failure due to deterioration will always produce conditions as good as new ones with an average of 1/mu1, while repairs of random failures may or may not achieve this. This assumption could easily be relaxed. The F0 status represents random failures that can occur at any time, but not while maintenance is being performed. Repair after random failures is completed at a rate of μ0 and then returns to the D1 state. The state space diagram of the maintenance model is shown in the figure. The figure shows the cost analysis for the replace and then do nothing scenario. Again, as has happened in the case of the probability of failure, the values are shown as functions of the delay of the action that varies in the range of 0 to 200% of the reference value specified by the user. The replacement cost, action, while not dependent on delay, is not constant on the chart due to net present value calculations. It is evident that delaying action causes more repairs as elements of the current repair policy before doing nothing comes into effect, so there are several notable jumps in the flow of maintenance costs. To find the optimal policy, the best action in each state must be selected. There are 2 actions to be taken. Action I, to do nothing. Action 2, to do maintenance. There are 2 times 2 times 2 times 1 times 1 times 1 times 1 times 1, 8 stationary policies to choose from the actions that can be chosen between D1 states, D2, and D3, whereas action I is available in states M1, M2, M3, F0, and F1. The optimal policy is expected, because the probabilities of the component transiting to failure state is getting higher in state D2 and D3. Also, the probability of deterioration failure, which is in state D3, is very high. The reward for the component to remain in D1, D2, and D3 states is 1,000, 900, and 800. The reward decreases from D1 to D3 because the component is deteriorating, and it may not work as well as new. The reward for the component to remain in states M1, M2, and M3 is -100, but for states F0 and F1 the reward is -500 and -1000, respectively. The figure shows the state diagram of the component for a case where the number of stages in the process is 4. The document, Adjusting Markov Models to Changes in Maintenance Policy for Reliability Analysis, is a reference of the application. Efficient and at the same time cost-effective maintenance is an important element for reliable operation in complex technical systems. The selection of the optimal maintenance strategy must consider numerous factors, including reliability and economic factors that are often equally important. On the one hand, for successful system operation, failures must be avoided, and this involves extensive and frequent maintenance activities. On the other hand, superfluous maintenance results in high and unnecessary costs. Finding a reasonable balance between the two is a key point for reliable system operation. The optimal policy is a set of decision rules dictating when and how maintenance should be performed based on the equipment's current state. One of the approaches that can properly incorporate all the above suppositions about the aging process and maintenance activities is based on state space Markov model, that consists of the states the equipment can assume in the process, and the possible transitions between them. The model of the Asset Maintenance Planner, AMP, that was initially developed and implemented by George J. Anders and Henryk Machewski. The AMP is designed for equipment exposed to deterioration but undergoing maintenance at prescribed times. It computes the probability, frequencies and mean durations of the states of such equipment. The basic ideas are the probabilistic representation of the deterioration process through discrete stages, and the provision of a link between deterioration and maintenance. AMP model observes that deterioration progress is represented by a chain of deterioration states D1, dk, which then leads to the F-fault state. In most situations, it is sufficient to represent the deterioration in 3 stages, an initial, D1, a minor, D2, and a major, D3. The latter is followed, over time, by a breakdown of the equipment, F, that requires extensive repairs or replacements. To represent the deterioration process, the equipment life curve is used, which shows the relationship between the state of the asset, expressed in engineering or financial terms, and time. This concept is easy to understand for a non-expert user who does not know the details of state transition models and Markov processes. The life curve corresponds to a Markov model that calculates the mean time to first pass, FPD, from the first deterioration state, D1, to the failure state, F, resulting in an average equipment service life, i.e., the length of the curve. Solving the model for condition probabilities calculates the expected durations of the states, determining the shape, i.e., the rate of deterioration in different phases of equipment where requires additional decisions on how the deterioration states are mapped with the ranges of asset condition values. Simple life curves obtained for specific models can be combined with composite life curves that describe complex maintenance scenarios. The second graph shows a scenario in which at some point preventive maintenance is performed, restoring the state of the asset, after which the breakdown occurs that leads to the replacement of the equipment. The curve is composed of 3 segments, and they do not need to represent the same models, a situation that can be modeled when a change in maintenance policy occurs, for example, after a repair. The Asset Risk Manager, ARM, uses the concept of life curve and discounted cost to study the effect of equipment aging under different hypothetical maintenance strategies. The results are based on Markov models adjusted to modified maintenance policies. This is done by pre-running the AMP program by an expert user. AMP and ARM are closely related and typically need to run consecutively. The implementation details of Markov models, the tuning of their parameters, and all other internal details should not be visible to the non-expert end user. The results are visualized through a life curve or through other concepts known from financial analysis. The figure shows life curves calculated by ARM for typical maintenance situations. In each case, the action is delayed by 3 units of time, e.g., months, and the analysis is performed for a time horizon of 10 units of time. In the event that a fault is observed in the do-nothing action, the equipment is repaired and its status is restored to 85%. The figure presents a Markov chain parameter estimation process, based on the following steps. It starts with the historical life of the assets, stored in the information system, to perform the preliminary data analysis. The result is the segmentation of equipment types. Subsequently, the characterization of the behavior of the equipment by segment is carried out. Predictive analysis is then performed to determine the projection behavior of the equipment by segment. For the new equipment, a classification model must be in place. Transition matrices should be modeled using equipment segments, which should be oriented to a Markov decision process. Finally, an individual asset maintenance analysis must be carried out, considering the specific characteristics of each piece of equipment, which will generate individual equipment decisions. Tribute to Hernando Duran Castro, my master's professor, in 1975, at the Universidad de los Andes. Nothing is necessary, nothing is enough, everything is useful. Always must learn. I add it. May he rest in peace.